Good evening, ladies and gentlemen. Today we have our president of the INCOSE chapter, Chesapeake, giving us a talk on INCOSE 2025 and INCOSE Chesapeake chapter's 25th anniversary. How will they align? The president is Taras Mykytyn. He retired from 35 years of federal government service, entered the private sector as a program director. He led multiple teams to address growing business penetration to DoD for IT and mission capabilities. He brought in systems engineering and program management expertise to developing business, technology capabilities, enterprise prizes for the contractors he consults for. His other accomplishments, he got an MS in engineering management, a minor in systems engineering from UMD College Park. He got DAU certificates from systems engineering and level 2 for program management from the National Intelligence Metric Unit, citation for Special Achievement Award. And he's got certificate of appreciation for mentoring Project Lead the Way in 2014 and subsequent years. So today he's going to talk to us about the global context for systems engineering, the vision for systems engineering in 2025. To you.
I'm Taras Mykytyn. I'm actually the president of the INCOSE Chesapeake chapter. I want to welcome everyone here. This is actually our first dinner presentation event for the year. We've got an exciting year coming up with our 25th anniversary. So the topic I picked for our first presentation is, with the INCOSE 2025 vision, how do we really align our chapter activities and what can we do to actually start furthering what INCOSE is providing us as what I consider a very efficient, very effective vision of where system engineering is going in the future. So real quickly, the state of systems engineering. A couple key areas: system solutions, theory and practice of system engineering, learn systems engineering, and applying systems engineering. The practitioner needs to be able to work in all those spaces. And the key thing is there's a set of engineering imperatives. And the key things here are we really have to expand the applications of system engineering across multiple domains. We typically do very well in the DoD and aerospace industries. And we need to broaden that out. And you'll see some more details on the areas that we need to broaden out our domain expertise and application across those domains. The other thing is the challenges we have, too, are embracing and learning diversity of system engineering approaches. There's not one approach or one methodology, one technique that'll be, the all-encompassing solution for all our problems. So we've got to make sure that we address that head on. And you'll see some of the further on slides that I'll talk about new technology and new ways of actually approaching the systems problems. The other thing is that systems engineering can really help shape related social and natural systems. Typically, we're not heavily involved in those areas, but as we find systems are more and more complex, there's an interdependency with social, economic, and environmental issues that we have to address and ensure that we include that in our system engineering solution space. Expanding the theoretical foundation for systems engineering. This is a broad topic. There are techniques, tools, and innovative areas that we can actually bring to bear to help us advance that. And I think we need to start looking at what are some of the key research areas that we should be addressing in the future. The tools and methods. There are a lot of good model-based system engineering tools and other system engineering complementary tools. But there's also additional techniques like big data analytics, machine learning, and artificial intelligence that can really help us advance some of the capabilities so that we actually can address the complexity of systems in the future. And the other thing, too, is stressing education. There's no reason that we can't really start getting people to start thinking systems think and systems, complexity analysis at an earlier age. We typically wait till either late in high school, undergrad or graduate school, and most system engineering programs are in the graduate level. we should really be looking at system think as a way for K through 12 to actually enhance the way they view the world and the way they view problems that they have to address. So the global context for system engineering. Key thing here, we have these 4 areas that we're concentrating on: human and societal needs, global trends, grand engineering challenges, technology trends. Those actually help us work through system and work environment trends and trying to address the complexity and where things are heading in regards to the work environment and the global trends that are out there. Another important chart, this actually covers where system solutions really provide us the foundation for how to address the complex problems, but they really need to be aligned to the needs of the society to satisfy those, as well as the needs of humans, and translate that into human factors and being able to work with the humans in society and bring them specifically capabilities that are not only of environmentally sound, but also from a human perspective in society, they're sound for them and acceptable in society. Okay, this chart just real quickly. We've always had environmental issues to address across the board. And the key thing here is that system engineering allows us to go in and, I believe, provide better solutions for potentially addressing areas in the environment, re-engineering medical and healthcare, and I'll go through some examples later on that. The transportation infrastructure, I believe that that's a prime area for future capabilities, since we actually have complexity in how we actually we progress with the urbanization of our cities, and also the amount of population that's expanding globally. And of course, we never can forget about integrating security and safety into society. This is actually an important role. It becomes more and more prevalent to address because of the potential impacts that we have on not only individuals, but people within our environment. Okay, some of the global trends. You'll see there's a stress on natural sustainability of resources, natural resources. This is actually key because we actually have to do a better job of looking at renewable resources and how to implement that and factor that into our engineering solutions. With increased globalization, that means that we have to communicate and be more interoperable across various domains and across various continents and industries, and that's a huge challenge. Our increase in population and urbanization. Challenge you have there is how do we sustain what we have today and grow that into the future as we become more and more densely populated in the cities, as well as population in certain countries expand. And now you need to provide clean water, food supplies, and general necessities of life. The increase in economic interdependencies. If you look at from the globalization standpoint, typically most companies do not exist specifically in just one country. They're typically globally distributed, not only for research, but for production and development activities. That whole interdependency drives the economic impacts on where we're going to be going in the future. And of course, changes in the environment. The more we develop solutions, the more we're potentially going to damage the environment. So we've got to take a step back and make sure that we actually address specifically the ecological impacts of systems that we deploy and capabilities we deploy. Some of the grand challenges, I'm not going to go through 14 of these in details, but key things to point out. We have to address large complex systems. Everything is getting more interdependent and globalized. We need to actually tailor technologies to not only local capabilities, but also regional capabilities, and potentially even at a global scale. That's going to be an interesting challenge in the future. We typically in system engineering address the full life cycle. The challenge is going to be even greater as we now have to take take into consideration the environmental, ecological, and social impacts of capabilities that will be deployed. The other thing is robust and sustainable implementation approaches. We can't afford to actually rebuild and re-engineer everything every single time we have to deploy a new capability. We really should be looking at how do we reuse components and how do we modularize things so that there's greater reuse throughout the engineering community and the products and capabilities that are put out there. And then the governance has to be stable so that we not only have cooperation at a local level, typically you need it at the country and or international and global level. So that's going to be extremely important too. Influential technology developments. Computational power is increasing tremendously. What you have today, for example, in everything from your cell phone to your smartwatches and technology like that, you couldn't even imagine that a couple years ago. It's literally capability of high-performance computing in a mobile device. So we need to figure out how to leverage that and actually engage with that. Human-computer interaction, key thing here is there are various ways of interacting with systems and managing the systems. And one of the things we have to do is figure out how do we control the interaction with those in a more advanced state. Software systems, more intelligence being built into the software capabilities that we have out there. Take, for example, and I'm an Apple person, so I've got an iPhone. You've got a chip in here called the A12 or Bionic chip. It's a machine learning chip and it allows you to actually embed and run specific software that's A, protects your privacy, and B, allows you to do advanced computing, things like image processing, basically any other functionality that you now have embedded in your mobile device, having to go to a cloud environment or pushing out more and more data outside of your mobile device. Sensor technologies are changing. GPS is the one example they give you. But you also have various sensors that are actually embedded in not only the health and monitoring of individuals and or capabilities, but you also have now Internet of Things is going to completely change the way we actually address and work with and interoperate between various systems and components throughout the world. Your refrigerator, you can buy those today. They're getting more and more smarter. They'll actually allow you to do everything from getting your full list of what's in your refrigerator to actually building out your buyer's list when you go to the shopping list. And it's all integrated now into the sensor technology as well as some of the new capabilities they have. Communication technologies, good news there is that it's becoming very easy to communicate. A good example is if you pick up your phone, you can actually have a chat with multiple people. I believe on the iPhone it's up to like 120 people. You can actually chat and interact with family and friends and or colleagues. So the technology is bringing us closer together in regards to working and collaborating in the future. Miniaturization. Key thing here is that you're now getting integrated circuits and system-on-system chips that actually have embedded in there much more capabilities than we typically have had in large compute systems and mainframes from the past. You've got world-class high-performance computing in your mobile devices at this point. Material science, this is another interesting area. There's actually new materials that are being developed that take on different properties depending on your environment and your circumstances. A good example, you're going to see clothing in the future that actually have embedded sensors, and it'll keep track of, as you're working out and or exercising, monitoring all your vitals and all your capabilities and providing that feedback directly, not only to your probably phone or a watch or a new technology that's coming out. It'll also allow you, if you okay from a privacy standpoint, to share that data with other individuals and or research institutes. Biotechnology, another key area. Genetic engineering, for example. Some of the things that we can do in that are pretty amazing. The challenging part here is how do you control the potential negative consequences if you don't have strict standards and or policies on what the biotech industry is allowed to do. Some of the system characteristics, sustainability, how do we actually make sure that the systems are sustainable and interoperable? Scalable, how do we take systems and apply them at different scales, everything from lightweight to globalized capabilities. Systems need to be safe, and this is part of the human factors implementation. How do we ensure that, for example, the phones that we build and or technology we build are not going to have a negative impact on individuals? I don't know if you've heard stories where people's phones actually flare up and or burst into flames. That's not a good thing. It's an undesirable result. Smart, now you're going to have embedded capabilities that allow you to actually not only develop systems that perform and complete the functional capabilities, but also they're tied in so that you can actually interact with and build the social and economic aspects into it. From a stability, again, systems actually have to have some level of mission assurance and resiliency. This is something that's a tough challenge for a lot of systems. A lot of people, they think they're going to build a system and that's all they have to worry about. But in this day and age, if you don't have the resiliency, you can potentially take out major services and or capabilities. Simple, this is part of being able to build fault-tolerant and reusable components. And again, security, some of the vulnerabilities that are out there. For example, integration or Internet of Things. There are a lot of great capabilities out there, but some of those are not secured. And there needs to be an awakening for not only the consumers, but the folks that are actually developing and producing some of the Internet of Things capabilities, that security plays an extremely important part. A good example is you do not want someone to be able to take over control of your car, either the brakes and or acceleration or other capabilities, without you being able to intervene. And that's been proven that's hackable, some of the cars that are out there with some of the advanced capabilities that are embedded. And then socially acceptable, again, this is pulling in from a social, environmental, and economic concerns, integrating that into your overall capabilities and systems. Engineering across application domains. As I noted earlier, we really focus on aerospace and defense, and as well as engineering in the DoD arena. These are other areas that are prime for advances in application domains. And in the future, we're going to actually, as system engineers, have to provide a more comprehensive role in working through some of the challenges out there. Current systems engineering practices and challenges, complexity is going up. That means we actually have to have better ways of understanding what the impacts are in interoperability and interfaces are. Typically, a lot of designs are actually done piecemeal rather than from an architecture. This is where model-based system engineering and other techniques can help develop architectures that are reusable, that we can actually share among other disciplines so that we actually provide a better level of interoperability. Knowledge and investment, lost at project lifecycle boundaries. This is a huge challenge. We typically have various disciplines, and I can relate to, for Department of Defense standpoint, you got program management and acquisition, you've got the engineering groups, including system engineering, and you have software engineering, testing, and operational support. In a lot of cases, those groups typically are not as intertwined as they should be, and that's something we got to look at to actually provide better synergy between the groups. Knowledge and investment lost between projects. This is where product lines and the concept of developing reusable components and being able to actually take those and generally take the functionality that you have, select that from a service catalog or a capabilities or product catalog, and either tweak and or make minor changes to it to deliver the next set of capabilities and new features that a customer wants. Technical and programmatic sides are poorly coupled. So your risk goes up tremendously if you don't have good synergism between your program management and your engineering teams. And this is something that I think system engineers can play extremely well in. And I think we're probably one of the few disciplines that actually typically work across all those boundaries. And this is just an example. If you're not taking into consideration the major risks and assessing those risks and really making hard decisions based on factual data, you're going to have issues like the major disasters for the Challenger and Columbia. Current SE examples. So when the 787 Dreamliner came out, Boeing actually modeled and provided simulation for all the major components before they even started developing and building any of those components. So they can validate and verify everything from stress points to interoperability between the various major components. And these were actually manufactured across multiple countries, multiple organizations, multiple companies. So they did an effective job in buying down the risk by actually providing the level of modeling simulation that you should have in a complex system as complex as theirs is. This one's an interesting one. So Ford is heavily into system engineering. They're actually model-based systems engineering allows them to actually cover the full life cycle on how they design, how they actually develop, and how they implement their capabilities. And that's coordinated and made available across all the various divisions that they have and their suppliers, so they know exactly who's building what and how it's going to play out. An example of system of systems engineering is the Thames Link rail capability. So the key thing here is that they actually took all the requirements, all the needs, and all of the interdependencies and mapped that out. So they actually understood what the potential impacts were going to be in pulling together the system and how to handle the volume of passengers as well as the scheduling of all their train systems. Composable design, this is interesting. So the Scania trucks, you actually pick and choose the various components that you want, and based on the reuse of those components, they actually build out specifically your capabilities that you need for your specific industrial use, and they've been very successful with that. Current state of systems engineering. So we keep evolving in response to a long history of increased system complexity. We are gaining more recognition across industries, academia, and other government entities. The practices vary across industries, organizations, and system types. And this is key, is cross-fertilization of practices will allow us to really be able to keep up with the global needs for system capabilities. Because right now it's outpaced the progress in systems engineering. That's something that has to be addressed. The practices are still heuristic-based. But there are a lot of new advances that theoretically we can actually cover. And yes, that is a V diagram. Integration, and that's for validation and verification of what systems engineering can bring to addressing complex problems. The integration across disciplines, this is also key too, to make sure that as we follow the full life cycle capabilities, we actually know how to represent and actually address the specific challenges across the board. Future state. This adds now more of the theoretical foundations, focuses on education, and starts looking at the gaps, and then how can we actually take the gaps and actually develop some major challenge cases that we can address jointly with other disciplines. And we really have to take the knowledge and skills that we gained from the Department of Defense and aerospace industry and look at how do we apply the same techniques, methodologies, and processes to other application domains. And then building out and addressing the trends that are occurring in system and work environments. By the way, I want to caveat, all these specific graphic images came from the INCOSE-CC Vision 2025 report and briefing slides. So I would suggest that folks actually read the specific documentation. It's a quick read, very, very well done, and it covers all these specific areas in more detail. Okay, I'm not going to read through these, but basically I'm going to give you sort of the highlight message. So applying system engineering across industry domains, we got to get to the point where, as I noted earlier, start addressing other specific areas that are pertinent to complex system development and complex engineering activities. Value-driven practices. This is where we tailor things to the specific domains. We scale to project size, so this can be anything from small to major complex systems, and scale to system complexity. Anything that has to do with multiple components or interoperability between major systems or components, or even interaction at a global level, we've got to make sure that we can scale and address those system complexity issues. Complex systems understanding. So this is where we should actually have insight through the appropriate metrics and monitoring capabilities to really understand what the behaviors of the systems are and make sure that we can actually mitigate undesired behaviors. Internet of Things actually, to me, is huge advancement. It's got a lot of potential. It's very exciting, but it's also extremely scary from a security and safety standpoint. So by monitoring and building out more advanced metrics and data analytics, we can actually start looking at, again, the performance and behavior of systems out there. Leveraging technology for system engineering tools. Key thing here is that you've got some tremendous compute capabilities out there and new tools. I don't believe systems engineering is caught up with that, but we have to start looking at, for high-fidelity system simulations, start leveraging cloud-based high-performance compute. For looking at visualization and understanding the complexity, interoperability, and the ConOps of systems, visualization and some of the new technologies there can really help us out. And I've seen advances in this where now you have things like, this looks like almost like Google's Glass project, but there are other capabilities out there, even in the past, that allowed you, oops. We lost access to it. My apology. Someone's going to come and help fix that real quick. Yeah, see, we probably got hacked or something. No, it's actually, I think there's another button out there. Okay. Stand still. Any questions up to now? I know this is a quick pace. Yes, sir.
Yeah, while you were talking, I was thinking of the federal government, and while you were talking, I was thinking of the federal government and whether systems engineering would apply to government, and if senators and congressmen were here, what you might say about lessons learned from systems engineering that could apply to social government.
So the challenge with social government is they typically, a lot of decisions are not based on data-driven decisions and decision-making. So I hate to say it, but putting a whole bunch of lawyers together to actually manage and operate and maintain the federal government, it's a nice concept, but it doesn't work in regards to decision-making. Politics needs to be taken out of the picture, and you need to really start looking at what are the models in the simulation of things that are impacting society, that are impacting the economy or impacting the environment. If you don't take that into consideration, then again, you're making decisions based on your own personal preferences and or biases, and that's not going to give you the solution that we need to actually advance some of the capabilities and things that we need in society. So, there you go. Partially back. So this slide for collaborative engineering, the key thing there is technology is there today. We have everything from desktop VTC to more advanced, you can literally bring up a session and whiteboard and share either presentation, engineering drawings, or anything else you want. And by the way, every company nowadays typically has these tools in place. And it really allows for virtual communications and collaboration across global boundaries and global access for the interaction. It allows for more effective collaboration and pulling together the solutions that you need to actually address the specific challenge that you're up against. See if this works, okay? System of systems design. Internet of Things, again, as I noted earlier, huge challenge. Interoperability, interconnection between computers and a whole bunch of endpoint sensors. That could be everything from your car to your appliances at home. Without safety and security built in, and without the ability to actually ensure that nothing is being maliciously actually embedded in the systems or someone's trying to take over your capabilities, this is going to be a huge challenge. So there's going to have to be new standards and new capabilities in driving out, how the interoperability needs to occur. And unfortunately, I think what's going to happen is that until you have a major incident and there's a major lawsuit, you're going to have most people ignoring security and safety in a lot of these components. Architecting from various viewpoints. Here's an example of the European Extremely Large Telescope. Key thing here is that we typically look at it from an engineering viewpoint. What do we need to build and design? And we also look at it from a supportability standpoint. But we really have a lot more different views that we should be looking at from a system perspective. We should understand the construction views. What does that really mean, and how does that impact what we're actually going to build and deploy? We should also be looking from a science view. What's the data, and how's the data going to be used? It's great to collect data, but if you don't know what you're going to use it for, what's the point? And then management view, of course, you've got to be able to provide insight into your stakeholders and your customers. And last but not least, providing also, I can't read that one. So again, when we build systems, we should be taking all those specific views into perspective and figuring out how to engineer to address all those. Composable design approaches. So this is where we can take various components, reuse them, configure and address how they actually fit into someone's solution space and operational space, and actually deliver an integrated and verified environment. This is actually very prevalent in software design nowadays, and the hardware approaches need to start taking this approach too. Resilient systems design. Oh, there we go, digital projections coming up. It's either good news or bad news coming up. We'll find out. It's good news. There you go. Thank you. Key thing here is that, and this is a set of drones that actually perform a certain function. Without redundancy built in, you could potentially have a failure of one system and actually all your capabilities go down. In this case, you've got multiple drones that actually can back each other up and provide interoperability and interconnection and communications between each one of those. Securing the system, key thing here, look at it from an end-to-end perspective. What do I need to address with all the touch points and all of anything that's going to impact my security? And that could be everything from the ticketing system all the way through getting through customs and or security at the airport, to working through, how do we handle the baggage and secure that, make sure that there's no specific either bomb material or chemical materials that are not supposed to be there, and then making sure that the communications between your aircraft carriers or transportation carriers and your ground control is actually intact. Data-driven decision making. So key here is decision support tools and the big data analytics that can help out. There is a tremendous amount of data that we typically collect depending on what industry you're in. And being able to visualize and actually present a summary of what's important specifically from that data to either the operators and or the end users is absolutely critical. And this is something that you should be flushing out earlier on in your designs, your use cases, storyboarding, as well as your early design. Virtual engineering. Nice part is that with some of the modeling simulation, now you actually have the ability of visualizing specifically and addressing what your components are going to either look like, what's the features and performance of those components, and how the interoperability is going to occur between those components. Here's an example of model-based system engineering. And the good news here is that if you do this correctly, your information is not only available from a system engineering perspective, but it also helps drive out software engineering, the testing activities, and your support documentation too, because you have a consolidated model and a consistent model how to represent what you're actually building. The other key technology is 3D printing and some of the capabilities that you can actually now generate and build your own components. This is everything from parts for automobiles and other industrial solutions, as well as there's capabilities being addressed now in the biomedical field where you can actually start building replacement parts within your body with specific tissue technology and growing out tissue technology and fabricating that. Theoretical foundation. So we typically focus on these areas right here, but we have to start taking in and start looking at advancing social and human sciences as well as natural sciences to help address the environmental and other application domains that we're going to be addressing in the future. Broadening roles of systems engineers. Never too early to start system thinking and teaching system thinking. Key thing here is that it really should be continuous education. You'll see that in a future slide, where we're actually starting at K through 12 and we're working through all the way through your full career as a professional engineer. System competencies. Here are specifically areas that can help round out your system thinking and provide more capabilities on how you're going to address complexity, how you're going to address the societal and the other impacts that you have with your engineering solutions. Building the system engineering workforce, and again, this is the start them early, build it out through various levels of your undergraduate and graduate work, and then continue on throughout your career to actually address system engineering and system think throughout your complete life cycle. In the future, so we are going to expand into more application domains. This is actually critical as we're trying to address and become globally competitive for all the specific areas. The sustainability from an environmental and economic and societal standpoint, absolutely critical for us to be able to broaden our horizons and be able to address things at a more global level and larger level. Socio-physical systems should be helping out in policy decisions. This is the question that you had in regards to why don't we have Congress taking the approach of using some system engineering practices? I think they should. I think that would help in some of the decision making. This is another area where we look at end-to-end life cycle to buy down risk. So you shouldn't really be thinking about, what software or what specific hardware I'm developing. You really should be thinking of, how do I push that into operations, and how do I support that and make sure it's operable and maintainable for the future. Collaboration, again, it's going to go across multiple organizations. It's going to go across regional boundaries and a broad range of disciplines. We've got, again, some great tools out there that we can leverage to actually start supporting this today. Model-based methods and techniques, absolutely critical, so we can actually reuse and drive out composable use of capabilities in complex systems. Enhancing our educational infrastructure, I think, is absolutely critical. The systems thinking part at all learning phases should be absolutely stressed. And then growing out the cadre of professionals. The good news with system engineering, you've got different levels of system engineering competency. I think the chapter does a very good job in helping folks prep for some of the tests, and then prepping also folks for the ESEP activities by mentoring them. So we got to continue that and expand that out into other technical areas. Path forward, look at the grand challenges. What are going to be the biggest things that impact us in the future? Look at establishing standards roadmaps. In other industries, this is absolutely going to be critical. Good example is the security and the Internet of Things. Who's going to actually develop those standards to make sure that security and the safety of some of these Internet of Things and components that are being deployed are actually interoperable and actually are safeguarding the end user? The system engineering book of knowledge. This is where we can evolve this to actually cover more application domains. Research roadmap, and this is where we can bring together the folks that are doing big data analytics, data science, visualization, and other key areas, and start embedding that into a research roadmap on where we need to be, 2 to 5 years out, as well as beyond. Education and standards roadmap, again, system engineering should be taught consistently across the boundaries. I'm sure Mr. McCarthy has some interesting stories on that, challenges on that, and how do we actually ensure that we're prepping the system engineers not only from the educational perspective, but also from a professional perspective, so that they can actually be effective when they get out into industry, academia, or government agencies. This is where I think we can engage and broaden our interaction with industry, government, and academic leaders. I think we do some of that in the chapter. I think we're going to get more aggressive this year to broaden that and make sure that we have better exposure and better interaction. A good example is that the University of Maryland, the student chapter, they mentioned that a lot of their folks are not clearable. They're international students. We need to figure out how to help them to find specific system engineering positions and make sure that we have the touch points and the relationships with industry and other partners to actually allow them to actually flourish and have opportunities to grow into positions in the future. How will the grand challenges be met? Core body systems engineering foundations. We need to have that taught consistently. This is where Mr. McCarthy can help us out and other folks. Complexity and associated risk is appreciated, characterized, and managed. This is where system engineering can provide the foundation for data-driven and model-based decision-making and buy down tremendously the risk in engaging with all the various partners and folks that have to develop the complex systems that we're going to be challenged in the future. The other thing is predicting the behavior for trusted, resilient systems. What we mean by that is to make sure that when we deliver capabilities, they're engineered where they're not only going to stand up from a mission assurance and COOP standpoint, but they're also going to be able to ensure that the resiliency is there too, so that as either performance increases are levied onto the system in real time, they actually will not fall apart and or break down. They're actually going to be expandable. A good example for that is some of the provisioning that can go on and some of the compute cloud storage capabilities and cloud processing capabilities, where you can, for example, take an assignment and provisioning of initial capabilities of certain amount of storage, processing, and compute capability. And as your needs grow, it dynamically actually allocates additional resources to help you manage that growth in a real-time fashion. Model-based system engineering, as mentioned earlier. This is actually critical since the complexity of the systems, you're never going to be able to understand them fully without having some model representing that. And we've learned in, I know, major DoD programs that this specifically, by generating modeling simulation, can save you tens of millions of dollars. And I was on one program where the challenge that we had was we had a technology refresh. And if we would have went through the specific selection and procurement of some of the new hardware that we were supposed to get, it would have cost us at least $10 million, and it would have been the wrong solution to actually meet the performance needs that we had. The modeling simulation flagged that and gave us the insight that we're heading down the wrong path. This is where, again, the recognition that we bring value for innovation and competitiveness. The only way we're going to be able to do this is if we actually consistently provide, good technical solutions and provide the insight into managing the risk and bringing down the risk for any of the complex systems out there. The other thing is, and this typically we don't do technology assessment policy analysis, this could actually help out across all industries. Anything from, I noted earlier some of the application domains, all the way through policies that are driven at federal government or state government levels to look at the trade space of what's the right thing to do in regards to either technology improvements, environmental improvements, and or impacts of deploying new capabilities. And last but not least, systems thinking at all levels, as noted earlier. What can we do? So these are all the categories that we discussed. We can now take a different viewpoint of them and start looking at them and looking through each one of those and addressing things like partnering with industry and academia and research labs to advance system engineering processes, tools, and technology. Establishing multidisciplinary forums. This is interesting because it takes various disciplines to actually address complex challenges. So we need to figure out who are the right people to partner with. And this can be not only in the rest of industry, the government, and academia. The other thing is, I think would be extremely helpful to advance system engineering methodologies and standards. Really develop either incubator and/or internships and joint DevOps environments to help us address that across the boundaries and across the board. Work through and work with the various students with consistent message on system thinking and how do we address system engineering in general through the curriculums. And then expand on training for system engineering tools. What specific certifications do we go beyond the ESEP? New research, advancing some of the key technology areas like AI, data analytics, and metrics and data-driven model-based system engineering to really help pull this all together from a technology standpoint and training the right people for the future. And that's it. Okay. Thank you.
Any questions?
So, hello? Yeah. So I think we all agree that we need to do more systems thinking. The thing that I'm a little unsure of is, I know what I mean by systems thinking. My question is, what do you mean by systems thinking?
So typically, engineering disciplines, everyone has their focus area and narrow niche. The systems thinking allows you to take a step back and look at the complexity of the problem and figure out and connect the dots on what the true interoperability is, true interdependencies, and how do we actually start addressing those, and how do we manage that effectively, and how do we put that into our project plans, software development plans, release plans, and support plans. So it's really taking a broader view of and understanding how to connect the dots. Some folks don't like thinking that way, but I think it helps them to understand if I've got a specific area I'm responsible for, one example is, software engineer loves to develop their software, their code. As soon as they're done, they throw it over the wall. Not all of them, but most of them. And it's someone else's problem to integrate, make sure it's interoperable, and make sure that it meets the end-to-end performance and or functionality.
Quick follow-on on that is, so how would you teach that in elementary school?
So take a simple thing as, say you have 5 children and they got to build something out of Lego blocks and or wooden blocks. How do you actually get all of them to interact together? And say one person's responsible for building something that's going to represent a house. Someone else is going to build something that represents a road. By allowing them to start thinking through what's the relationship between a house and a road and other components, allows them to start thinking at a broader and more larger level to place all the interconnections and connect the dots. Kids are pretty amazing if you give them the opportunity and you challenge them. Good example is if you take elementary school orchestras, listen to them beginning of the year, absolutely everyone's out of key, everyone's playing who knows what. If you have a good band director, they can actually get everyone to understand what the role is and how they actually play harmoniously together to actually play a musical piece. And I've seen that, with my children growing up, where, the beginning of the year, they start out and you just shake your head going, oh, this is going to be painful. But by the time they're done, middle of the year and end of the year, they're actually playing some very, pretty sophisticated pieces, and they actually sound pretty good.
Yeah. Well, I have a question. As far as kids are concerned, also the exposure, to certain facts and about cooperation. One of your slides I couldn't see due to contrast in the lower left, collaborative. Could you bring that up again, if possible?
Can we bring up the slide deck again?
Well,
Hit the backward.
Okay.
yeah, it's about halfway through.
Oh, I'm going to be clicking here for a while. Next question.
Oh. Okay. The question with that is, we used to have first the integrated and enterprise process 20 years ago at Northrop, approximately, and IEEE, the different divisions, like where there's a cross-discipline EMC, microwave antennas. James Lynn and a bunch of guys back in 16 on the Microwave magazine were talking about that. And the issue there is, I guess you could, definitely have something like that in INCOSE between the different workshop groups.
Okay.
If you can have a linkage and the intersection of some of the disciplines, depending on the program. So, I was just curious about this.
So let me walk you through an example. This is something on a major program I was involved in. We were building one of the, I would call the biggest database in the world. And the challenge that we had was how do we synchronize folks that were working in different geographic regions? How do we coordinate and provide information and sharing of information and tracking of information and engaging with the right level of engineers and or other technical talent? So we literally had a system, an information management, data management system that allowed us to collaborate on a whole bunch of different levels. So we can tell you exactly who had access to and who touched any of the documentation. We can actually collaborate and actually mark up documents in real time online, and we could share that information to whoever needed it. So we can protect things that were sensitive, programmatic things and funding. We can share things like technical specifications, ICDs, architecture diagrams, and all that was available. And this is back in the late 90s that we had this capability. I use SharePoint extensively, and I have for the last 10, 15 years. Be honest with you, either we have crippled SharePoint and the environment that we're in, or the tool just doesn't give you half the capabilities that we had originally. And that's disappointing.
Yeah, so we have to get the program managers, we've got the board members to be signed in, and so can I ask you to hang on to the questions a little bit? You could also talk to him after the presentation, because we've got to get that done, right?
Okay, that's fine.